we're going to look at a case here. This is the NEXit trial. NEXit is a intervention for smoking cessation, which is delivered by text messages. It was designed to target university students in Sweden. It was a few years back now, so the results are published. You can read about them here. So these were the main results, and then there was a second paper that looked at heterogeneous treatment effects. And what I'm going to show you below is really the second one, where we looked at the calibration of the model used. This was a randomized controlled trial. We're going to talk about that later, but basically we allocated people to receive the text message intervention or a waiting list control design. The outcomes were 8-week prolonged abstinence was our primary outcome, which we defined then, or which is traditionally defined as not smoking more than 5 cigarettes the past 8 weeks. So you're considered a non-smoker, so to speak, if you haven't smoked more than 5 cigarettes the past 8 weeks. What we found was, this is sort of an excerpt out of the results. At follow-up, the number of participants reporting prolonged abstinence in the intervention group was 203 out of 783, so 25.9%. And in the control group, 105 out of 719 reported prolonged abstinence. An odds ratio of 2.05 was given by unadjusted logistic regression, and 2.05 with a difference confidence interval by adjusted logistic regression. So there seems to be something going on. The interventions seem to help people quit smoking. And we could then say, well, let's assume you're working at the student healthcare center, okay? And 3 students come into your office at different times, and they all smoke, and they want help to quit smoking. Then you could say, well, if you sign up for this NEXit intervention, you'll have a probability of 25.9% of quitting smoking. And if you don't sign up, the probability of you quitting smoking is 14.6%. Another question is, are you lying? Is that true? Because you've used the data from a model here that says one thing, and now you're making a prediction. You're predicting what's going to happen with these 3 individuals. But for you to really know that these predictions are good, you need to check the calibration of the model. You shouldn't just rely on what it says here. So we did that in the second paper, looking at the calibration of the model. Inside the boxes, I'm mixing bins and boxes here, but I mean the same thing. When we looked into it, we found that the predictions of this model, which you were using here to make predictions, was really good. There were 2 bins that people were put into, a 21 to 30% bin and a 10 to 20% bin. And these red dots show you that when we predicted a 14.6% probability of smoking cessation, that's also what we saw in the empirical frequency. So that's what we saw. And the same thing with among those who we predicted quitting smoking with 25.9% probability, that's also how many actually quits. This line here shows you the perfect predictor. So any deviations from this line means that your model isn't making a perfect prediction. It's different from perfect. And in this case, our model was making perfect predictions. Great. So you're not lying. You're not lying to the students that came in. This is sort of likely the best you can do in making a prediction at that time. It's a bit anticlimactic though, because you're really just giving the same advice to everybody that shows up in your office. Anybody, despite of how long they've smoked and how old they are, you're giving the same prediction to everyone. And we'd like to do better. We would like to do something a little bit more personalized. But then you see, well, they actually had an adjusted logistic regression. So they had a model that actually took into consideration sex, number of years smoking, number of cigarettes smoked weekly, severity of dependence, and the amount of snuff used at baseline. Wow, okay, so I can use that model to make personalized predictions then. I can just input this information about each student, and I'll get a different prediction for each student, and that way we get a more personalized prediction. So we'll look at the calibration of that model, the adjusted model. To do that, I'm going to have to redefine the bin size issue here. So when I introduced cross-validation, I arbitrarily picked bin sizes. So I picked 0 to 10%. But why couldn't I use 0 to 5% and 6 to 10%? Or even 0 to 3%, 4 to 5%, 6 to 8%, 9 to 10%, and so on. I could break down this bin to multiple bins of different sizes or smaller sizes. And calibration plots are going to matter depending on which bin sizes you pick. Now, put that issue out of your mind, because we're going to solve it using something called locally weighted scatterplot smoothing. It basically means you don't have to pick the bin sizes. We're not going to go into detail of how this looks, but essentially you can ignore the fact that bin sizes have to be picked. You don't have to do that. You can almost think of them as if you have an infinite amount of bins, okay? So let's just forget about that. Don't worry about the fact picking bin sizes is not an issue. Okay. So back to the question. I have an adjusted model. I'm going to use that one to personalize my predictions to my students so that I don't give the same advice to everybody. Let's look at the calibration of that model. It's terrible. Okay. Here we have a perfect predictor here. And this red line represents the calibration of the model, or the predictions of the model. And it looks okay here, but here it really goes off. You can see here that for some individuals, it's predicting that you'll have a 55% probability of quitting smoking. But when you look at what these individuals actually had, they had a probability of quitting smoking just higher than 30%. So because this red line is not fitting this diagonal perfectly, we have poor calibration. And it seems to sort of do well here, but then it just goes nuts over here. So what we should take from this is that our adjusted model had poor calibration. The algorithm that we used to estimate that regression model in the paper is not good at producing models that make useful predictions. The model itself might be useful to describe and explain the population, but it's not good at making predictions. So don't always assume that models presented in a paper or an article are good at making predictions. Always ask for an evaluation of the predicted performance. Especially if authors are saying something about prediction, then you should see something like this or some kind of evaluation of the predicted performance. So I said that the algorithm that we used wasn't very good at creating a model that does good predictions. So in this paper, we looked at actually making a model or using an algorithm that was better. You don't have to understand this. I just want to show you what such a model would look like mathematically. And we did that, and we found that this model and the algorithm we used to learn this model allowed us to make much better predictions. You see the red line now is much, much closer to the perfect predictor. It still does veer off here, but it's not close as bad as this. This is terrible. This is a little bit better. And you can read more about the model itself and the whole setup of this experiment, and the paper is linked here.